Hi. Anaglyphs. They can be used to enhance the illusion of a third dimension on a screen when wearing glasses with colored filters and a different color for each eye. There are several color couples possible, each with its own properties. And seemingly there are a few real applications to this. However, I also love simply looking at them without such glasses, just because it's so buggy. My test image for this will be this photo I learned to love, which I found on Unsplash by Bao Menglong. Let's dive into the code. First, I don't know the pixel format, nor the file format of the input image, so instead of reverse engineering all image formats just for compatibility and re-decoding the wheel, I'll just be using the image crate, which, among other things, decodes and encodes every common file format. Then we can list some color couples, at least those from this Wikipedia article, in an enum. I also handpicked the colors from that table and stored them in constants. Our library should create an anaglyph from an image with one function call. By the way, documenting is not only useful for the future self or the person discovering the project, if any, but also to clarify things when coding by putting them into words and checking what you are doing even makes sense. We should document. What the user should be able to do is simply to provide the name of the input file they have, the output file they want, the X and Y offsets between the two color channels of the same image, and the two color channels, which is a value of our enum. We could also give the choice of the two colors as RGB arguments, but I'll stick to this to know what the presets look like. We must allow negative offsets, so for later purposes, determine the direction of the offsets. Match the left and right colors with the given enum possibility. In order to work with the image data, I will open the image and get its raw buffer of RGB values, 24 bits per pixel, a pure vector of unsigned integers between 0 and 255 for each red, green, and blue channels for each pixel of the input image. The output size will be the initial size minus the offset, horizontally and vertically. Now, when filling the outbuffer with our custom integers, we'll often need the same values, thus create a struct containing what we'll need. After instantiating the struct, fill the outbuffer and save the output with the given file name encoding with the image crate. In order to fill the outbuffer, I have an awesome drawing here, warning expensive software, that helped me determine the indices of the two values I want from the input buffer relative to one index in the output buffer, using the offsets, the lengths, and the direction. To explain how I see it, there are two imaginary buffers which will overlay on each other, and the color I want for each pixel in my output buffer will be an average of the two colors from the two imaginary intersecting buffers on that pixel. And the clutch is that those two imaginary buffers are actually the same buffer, which is the input image. Wow! This is done for each R, G, and B for each pixel of the output buffer. With this overlay of the input buffer with itself, keeping the intersection of the two will result in seeing all pixels of the input image in at least one color channel, as long as the offsets are lower than half the length of the side, in which case a middle line or a middle cross would be unrepresented in the output image. In the process, I realized how fun, keep things in their scopes, it can be to work with images when programming. You can get astonishing results that you didn't expect at all, or at the very least, original outputs. Back to it, let's see how to get those values if the offsets are towards a bottom right angle. The imaginary top left buffer's index we seek will be the index in the output buffer to which we add. First, the vertical offset times the input width, plus, secondly, the horizontal offset times the number of rows of the output buffers we've filled, plus 1, as the offset is on the left, so we count them before filling a line. These two times 3, as we defined offsets and lengths as a number of pixels, and we have 3 integers per pixel. The imaginary bottom right buffer's index we seek will be the index of the output buffer plus the number of filled rows computed as the quotient of the division of the index by the length of rows. And there we have it. With the same logic for each direction, which is bare inversion in some way, we're able to get the two color values we want depending on the direction of the anaglyph offsets. This is for sure optimizable, but for readability, kinda, I'll keep it that way. All I want is for it to work. It could also be done on the GPU with textures, shaders and frame buffer blitz if we really want performance. Encoding full videos will for sure require this to be done. If you want to see me do just that with OpenGL in the future, I'm down. Now that we can collect the values from our imaginary buffers, we'll fill our out buffer with, for each one of its integers, an average of the two collected values times the R, G or B value, which are between 0 and 1, of their color filter, depending on their position in the out buffer. And that's it. Add a few tests to generate anaglyphs, and here are the results. In fact, the smaller the offset and the subtler the change, the more disturbing it is to me. Also, I realized that people on zoomed photos look like the Dead Cell's main character, with a chill skin. Especially on these anaglyphs, with strong bright color filters and what looks like ghosts, no spoiling. And now we can publish our Rust library on crates.io. And now the sponsor of this video, Wikipedia. Just kidding, go read an article.